Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. In this episode, we're going to talk about periodic trends, which is Chapter 3 of the IB Chem SL curriculum. So, either to your happiness or your to dismay, there are going to be very few calculations in this chapter, more terminology and concepts. And so, here are some of the essential ideas, understandings, guidance terms, and application skills that we are going to see for specifically 3-1, the periodic table. So the first thing we have to do is determine electron configuration based on the periodic table. We kind of did this in chapter 2, but remember that these are the s orbitals, these are the p orbitals, these are the d orbitals, and these are the f orbitals for the lanthanides and actinides. Here is another graphic to kind of show that. Now notice that if I were to do the electron configuration for hafnium, I would have to go from the 6s2 and then 57 to 71. I have to fill in this f orbital before I get to the hafnium, which is 72 there. So talking about the periodic table, some important parts of it that we have to identify. We've got the alkali metals here. We've got the halogens, which is group 17. The noble gases, which is in group 18. We've got the transition elements in this D block here. These are the metals. And we've got the lanthanides and actinides here at the bottom. Another important group that was not on that periodic table were the semi-metals here. I think aluminum is not included in this. But the semi-metals here, also, it's important to be able to distinguish between metals and non-metals. Here we have alkali metals, alkali earth metals, transition metals, other metals, and these are our lanthanides and actinides, which are also metals. So these are all metals, even though they're called different things. They all fall under the category of metals. Now, talking about metals and nonmetals, here are some characteristics that differentiate between the two. Semi-metals have properties of both, but are a little bit closer to the properties of nonmetals. Now, one thing we are going to talk about is that metals tend to lose electrons, while nonmetals tend to gain electrons. We'll talk about why that is more later. Again, here we are. This is correct. So here are the actual metalloids in this kind of, I don't know how you would describe this color. This kind of like dark, or it's not even dark. I don't know. I don't know how to describe that color, but kind of like a green, darkish green. I don't know, but just some of the players or the groups that we see in the periodic table. Okay, so here is a version of the periodic table. It might look weird, but that's because the D block is taken out completely. So we see here normally it goes from 1, 2, 1, 2, 3, 4, and then 5 is all the way over here. So all it's done is taken out the D block so that we can bridge beryllium right next to boron, and we see that right here, beryllium right next to boron. So it turns out that in the periodic table is a lot like high school, where we have cool kids, and everybody is going to try to be like the cool kids. And the cool kids are these guys right here, the noble gases. And the reason that they are so cool is that they have their valence or their outermost shell completely filled with electrons. We see here 2 is the maximum that we can fit in the first shell because 1s2, and so helium has 2 electrons. In the second shell, we have 2s2 and 2p6, so we can also fill 8 electrons in there. In this next one, same thing, 3s2, 3p6, so we have 8 electrons there. And all of these other elements are going to, we'll talk about this more in bonding, but are going to beg, borrow, and steal whatever they can do in order to become like the noble gases. That's why chlorine gas, was used in World War II to cause havoc on the battlefield. You see, chlorine here only needs one more electron to be like argon. So chlorine is going to do whatever it takes, rip electrons from other elements to get that one electron. And also gives us insight into the bonding of these various elements. So chlorine is going to have a -1 charge because if it's an chlorine ion is going to have a -1 charge because it only needs one more electron to become like argon. Oxygen and sulfur are going to have a -2 charge because each of those needs 1, 2, 1, 2, 2 electrons to become like neon or argon. Nitrogen's going to have a -3 charge, and so on and so forth. Now, lithium and beryllium over here, the alkali and alkali earth metals, they've got two ways that they can become cool kids. So lithium has a choice. He can either gain 7 more electrons to become like neon, or he can lose this 1 electron to become like helium. And so the easier route, since, if lithium was smart, is all he would do is lose this electron instead of trying to gain 7 to become like neon. So lithium's going to want to lose this electron. And since he's going to lose his electron, he's become more positive, which makes him a cation. So the charge of lithium is going to be +1. The charge of beryllium has 2 of those electrons. It's easier to lose those 2 electrons than gain 6 more and become like neon. And so we can also tell that everything in the same group has the same number of valence electrons. So lithium has 1 in the outer shell, sodium has 1 in the outer shell, potassium has 1 in the outer shell. So they're all going to have +1 charge, and they're all going to react similarly. Same thing with beryllium, 2 in the outer shell, magnesium, 2 in the outer shell, calcium, 2 in the outer shell, fluorine, 7 in the outer shell, chlorine, 7 in the outer shell. So in the same group, you're going to have the same number of electrons.